US Physics Olympiad, year 2020, USAPHO, final round. Problem B1. String cheese. Question A. When a faucet is turned on, a stream of water flows down with the initial speed v0 at the spout. For this problem we define y to be the vertical coordinate with its positive direction pointing up. Assuming the water speed is only affected by gravity as the water falls, find the speed of water v as a function of y at the height y. Define the zero of y such that the equation for v square has only one term, and find y, the height of the spout. Question B. Assume that the stream of water falls from the faucet is cylindrically symmetric about a vertical axis through the center of the stream. Also assume that the volume of water per unit time exiting the spout is constant, and that the shape of the stream of water is constant over time. In this case, the radius r of the stream of water is a function of vertical position y. Let the radius at the faucet be r0. Using your result from part A, find ry. If ry is not constant, it implies that the water has some radial velocity during its fall. In contradiction to our assumptions in part A that the motion is purely vertical, you may assume throughout the problem that only such radial velocity is negligibly small. Question C. The water-air interface has some surface tension sigma. The effect of surface tension is to change the pressure in the stream according to the Young-Laplace equation. Delta P equals sigma multiplied by 1 over small r plus 1 over big R, where delta P is the difference in pressure between the stream and the atmosphere, and the big R is the radius of curvature of the vertical profile of the stream visualized below. R less than 0 for the stream of water. The radius of curvature would be positive only if the stream profile curved inwards. For this part of the problem, we assume that absolute value big R much greater than absolute value small r, so that the curvature of the vertical profile of the stream can be ignored. Also assume that water is incompressible. Accounting for the pressure in the stream, find the new equation relating for Ry in terms of sigma, R0, V0 and ρ, the density of water. You do not need to solve the equation for small r. Question D. After falling for some distance, the water stream usually breaks into smaller droplets. This occurs because small random perturbations to the shape of the stream grow over time, eventually breaking the stream into a part. For the rest of this problem, we ignore the change in the radius of the stream due to changing speed of the water, as considered earlier. Instead, we examine small random variations in the radius of the stream. Random variations can be broken down into a sum of sinusoidal variations in stream radius, each with a different wave number k. We can analyze these different sinusoidal variations independently. Consider a stream of water whose radius obeys ry equal r0 plus a cosine ky, where a much less than r0 is the perturbation amplitude. To analyze such a stream, it is sufficient to consider only the thickest and the thinnest parts of the stream. According for both sources of curvature, find the condition for R0 and K such that the size of perturbations increases with the time. Solution for problem B1. Question A. We can use energy conservation to answer this question. For a bit of water with mass m, the total energy E is the sum of the kinetic and the gravitational potential energy. E equal 1/2 mv square plus mgy. With this sign convention, g approximately equal 10 meters per second square is positive. As y decreases, so does the potential energy. As the bit of water falls, its energy remains constant and is equal to the initial value. So E equal 1/2 mv0 square plus mgy0. Let's equate them. We have this equation, and solving for v, we have v equal square root from v0 square plus 2g multiplied by y0 minus y. The equation for v square has 3 terms, but we are asked to choose the 0 of y such that there is only one. Evidently, 2 of the terms must cancel, and this must be the 2 constant terms, since the final term varies with y. That means that we need v0 square plus 2gy0 equal 0. Solving for y0, the vertical position of the spot is y0 equal negative v0 square over 2g. With this choice of the 0 of y, the equation for v simplifies to v equal square root from negative 2gy. We know that the result of this equation is real because y less than 0 at the spot and decreases as the water falls. So this equation shows that v is real and increases as the water falls. That was a solution for question A. Solution for question B. The same volume of water must fall through any horizontal cross-section of the stream each second, because water doesn't disappear during its fall, and its density is constant. That volume per unit time q is cross-sectional area of the stream multiplied by the speed of the water in the vertical direction, which give us equation q equal v pi r square. Q is the same at all y and is equal to its initial value q. So we have q equal v0 pi r0 square. Now equalizing these two parts, we have expression for radius r as a function of v, and plugging v from question A, we have that radius r is such function of y. That was solution for question B. Solution for question C. Conservation of energy approach from part B needs to be modified to account for the work done against pressure. As we look further down in the stream, the radius is smaller. This means the pressure is higher there, and the water is slowed compared to when we assumed only gravity acted on the water. The result of accounting for changes in pressure in a flow where no energy is dissipated is the Bernoulli equation. Here P0 is the pressure in the stream at the spot. Using the Young-Laplace equation to replace P and P0, delta P equals sigma multiplied by 1 over small r plus 1 over big R, we have this one. If we substantiate y0 and v as in previous parts, this equation becomes this one. This last one could be simplified to this one. which is an indirect equation to connect r as a function of y, which we don't need to solve. That was solution for question C. Solution for question D. If the size of the perturbation increases with the time, water must be flowing from the thin parts of the stream to the thick parts. For that to happen, the pressure needs to be higher in the thin parts of the stream than in the thick parts of the stream, so that the pressure gradient will force water towards the thick parts, eventually breaking the stream into droplets. We consider a small patch with a side length h on the surface of the stream at the thinnest part of the stream. The pressure is delta P thin equal this expression, and at the thickest part this expression. We are looking for the water numbers such delta P thin greater than delta P thick. To simplify this further, we will need to find small r and big R in terms of A and K, the variables given in the problem statement. A small r is the thickness of the stream, which from the equation given varies sinusoidally. R thin equal R0 minus A and R thick equal R0 plus A. We are going to need 1 over R to use the Young Laplace equation. 1 over R thin approximately equal this one, and 1 over R thick equal this one. The inequality now like this. Next, we need to determine the radius of a curvature big R of the sinusoidal function and circle at the small deviations from the thickest part of the stream. Recall that for small theta, cosine theta approximately equal to 1 minus 1/2 theta square, which means that y sinusoidal equal a cosine kx, which is approximately this. Next, we consider a circle of radius big R. If a particle moves along such a circle at speed v square over r. This means that if the particle moves forward for a short time t, moves forward a distance vt, and falls at distance 1/2 v square over r multiplied by t square. If we set vt equal x, then the y position of the particle y circle approximately equal y0 minus 1/2 x square over big R. Comparing, they give the same a k square equal 1 over big R. We have 1 over R thin equal negative a kx square, and 1 over R thick equal a k square. Putting this into the inequality, and this simplifies to k less than 1 over R small. So the perturbations will grow as long as they have a wave number greater than 1 over the radius, or equivalently when the wavelength of the perturbation is longer than the circumference of the stream. This result was discovered experimentally by Plateau and derived theoretically by Rayleigh. The breaking up of a stream into droplets is called the Plateau-Rayleigh instability.